In this video, we're going to continue our discussion of simple linear regression, moving into some discussions of some other statistics we can calculate with regards to these models, as well as some of the statistical significance tests we can conduct. So first of all, it's important to realize when we were in the ANOVA chapter, we talked about the fundamental ANOVA identity. That is, the total movement of the data from the grand mean can be described as the movement from the group to the grand mean plus the movement from the individual data point to the group. In this particular case, we can actually use this same idea with regression, but instead of talking about the grand mean and the group means, we're now going to be talking about the grand mean and the individual line, which is itself a prediction of that particular data point. So now we have the data point to the grand mean can be calculated, or the overall mean, whatever you want to call it. We don't really have a grand mean in regression. Can be broken into two parts, the movement from the line to the mean, as well as the movement from the data point to the line. So data point to mean can be described as movement from the data point to the line, and then line to the mean, so it can be broken down into those two sections. Now, why would we ever do this? Well, there's two reasons, one of which is we're going to be able to test the overall effect of the model. Now, in simple linear regression, that's not going to be particularly useful, the test of the overall model. That is anything in the model working? When we only have one independent variable in the model, that's going to tell us, well, is that one independent variable contributing anything? So that's not going to be much more useful than our individual variable test that we'll also talk about. However, what we can do in multiple regression is we can test the contribution of multiple independent variables all at the same time, and this is useful. So when I drop in a bunch of independent variables and I want to see, is anything working? That is this model performing at all? Is it doing any level of prediction? We can say yes or no. Now, on the topic of prediction, just like we could break down kind of the different sums of squares when we were talking about ANOVA, we can also do this in regression. Now, thinking about this, we have the total movement, the movement due to our model, and the movement due to the error. So what we can do is take the movement due to our model over the total movement and say what percentage of the total movement is due to the movement as it is respected to our model. So the total movement, what percentage of the total movement is due to the model? In this particular case, this is called a coefficient of determination. You'll see this written as lowercase r squared or capital R squared, depending on if it's a simple linear or multiple linear regression. And this is interpreted as the percentage of the variability in the outcome that's explained by the grouping of the independent variables, or in the simple regression case, by the single independent variable. So just as an example, I plugged in some numbers from our previous example that we walked through. So we had 110 was the sum of squares regression, and 114 was the total sum of squares. So 0.8772 was the number that came out on my calculator, and 87.72% of the variability in the outcome, in this case number of cars sold, was explained by TV ads. Now this is interesting. They do add the caveat that this is linear. That's absolutely true. When we look at this variance explained, this is the linear relationship that's explaining that variance. But it is cool that we can say, well, 80% or 87% of the variability in the number of cars we're selling depends on the number of TV ads. This is pretty promising because what this means is that, things like weather, things like what mood people were in, those are things we talked about previously. If this were the case and this were the model, those would play a lesser role in the number of cars sold than TV ads. How do I say that? Well, I can see that the maximum variability left for those things to account for is like 12% of variability, 13% of variability. So the maximum that any of those could account for, actually all of them together could account for, is 12 or 13% of the variability. And the TV ads is explaining 87% of the variability. So it's way more important than anything else that could possibly be there. So this would be very good news for somebody looking to consider TV ads. I guess I should be careful when I say that. This would be very good news if adding a TV ad was not like made me money. So I think in the previous example we had 5 cars sold. So if the profit from the cars sold exceeds the cost of the TV ads, this would be very good news. But if the profit from the cars sold did not exceed the number of TV ads, this could actually be pretty bad news. This would say, well, yeah, your TV ads are what's primarily driving your number of cars you're selling, but gosh, if you start adding TV ads, you're going to lose money because you're not selling enough new cars because of that. So that'd be a bad case. So again, in this case, we're saying that the 87% of the variability in cars sold is related to TV ads. I don't want to say is due to TV ads. And in fact, even the question as to the direction is not necessarily clear from this. So maybe it's 87% of the variance in TV ads is due to cars sold. And actually, in this particular case, that in the simple linear regression case, the direction isn't specified. In multiple linear regression, it is a little more specified. We can also calculate a correlation coefficient. This is the most awkward way I've ever seen a correlation coefficient calculated, but we can take the square root of the coefficient of determination. That's that variable we were just talking about with the percentage. So in our previous case, the coefficient of determination was 0.877. So I could take the square root of that. Then you also want to add the sign of the slope. So correlation, the coefficient of determination is a percentage. We don't have negative percentages. It's just one direction. But correlation does have a direction. So it can be a negative or a positive correlation. And we just add that sign in front of this here. So in this particular case, the sign was positive, 5. The square root of 0.8772. I add the positive sign, which we don't usually write. It's kind of there invisibly, and I get the correlation as 0.9366. This is a super awkward way to calculate the correlation. It makes sense if you already have the coefficient of determination r squared, but what's typically done is you calculate the correlation and then you square the correlation to calculate r squared. So that's typically how you calculate this. All right, so in this chapter, we are finally going to get around to talking about error and checking the assumptions that we make about error. We have made these assumptions through several of our analyses, the biggest one being ANOVA. And we talked about these in ANOVA, I believe. But here we're finally going to get around to actually checking these a little bit. Now, it's important to realize that numbers 2 and 4 are the ones that are tested using a statistical method. So 2 and 4, we might run a statistical test on. There are statistical tests. I prefer using plots. Plots are strangely, I mean, people think statistical tests are the best thing in the world, and as a stats person, think I should believe that too. But actually, graphical methods for testing assumptions are probably, in my opinion, the best way to test assumptions. Because they work well under a variety of different circumstances that the statistical tests, all of them break at some level. So I prefer using methods that work well. The catch with graphics is it takes a little bit more training to use. And by a little bit more training, I don't mean, oh, you have to have a PhD in statistics. What I mean is you have to spend half an hour looking at it. So this is something you can absolutely learn to do, and because of that, that's the other reason I prefer statistical graphical methods in assessing error terms as opposed to preferring statistical tests. Statistical tests you can do in a couple minutes. Graphics take a little bit more time, but again, the graphics are going to give you all around a better interpretation of your assumptions. All right, so that's 2 and 4. What happens with 1 and 3? Well, number 1, the error is a random variable with a mean of 0. If we use the least squares criterion, then this is always going to be true. So this is an assumption, but you can go on and put a little check plus. If you used least squares, it's done. Ta-da! Yay! I'm done. Okay, so this is good, but this is important to realize that actually we do meet this through least squares. How about number 3? Where do we meet number 3? Well, number 3, as we've talked about in the ANOVA section, is actually met through the study design. did you collect data points that were connected to each other in a way that's not included in the model? So the common examples of this are like, did you collect data from brothers and sisters and not account for that in the model? Did you collect data from twins or something like that and not account for that in the model? Those would be cases where we would be violating independence. So if you didn't do that, you can also put a little check plus. If you just randomly sampled, that's the best way to meet this condition of independence. A random sample from your population of interest is a good way to do this. And actually, in a random sample, even if you do accidentally get a brother or sister, we treat that as independent. If you did a random sample, typically you're good to go here. So these two, number 1 and 3, number 1 is always true. Number 3, I would check my study design. In a textbook situation, though, it's really hard to check study design. So in class, we actually don't check number 3 all that often. We focus on 2 and 4. But in your research, realize number 3 is accessible. That is, we can look at it. We just look at the study design. We don't look at statistics typically. All right, well, let's talk about statistical tests. We are in a stats class after all. So remember, our tests of significance determine if these values are greater than or less than or not equal to some specified value. In this case, we're going to really focus on being not equal to 0. That is, we typically do a two-tailed test. We do t-tests for the individual values, individual parameters. So remember, our parameters that we're testing are beta 0 and beta 1. So we do a t-test for beta 0 all by itself and a t-test for beta 1 all by itself. And then we use an f-test to kind of test all of them together. Now we do require an estimate of the overall variation. So remember, in like our z-test, we needed somebody to tell us sigma squared, and then in a t-test, we needed to estimate sigma squared. So in this case, we're going to estimate sigma squared, but we have to do that using the model itself. So this is a little bit interesting. How we do this in ANOVA is we took the SSE divided by its degrees of freedom. Actually, in regression, it's the exact same thing. Take the sum of squares error divided by the degrees of freedom of the sum of squares error, and that gives you your estimated variance. So in this case, we call it the MSE, or mean squared error. And this is what we use for our estimated variance. Recall we did this in the basic t-tests very beginning of class. The only difference is now we're using a bit of a more broad definition of variance to make this calculation, but we're still finding the same value that we needed for our t-test. All right, so once we have this, we can take the standard error of the estimate. This is going to be important as we do a calculation for the standard error of our particular estimates. So this is kind of like a general thing, and then we have to differentiate this for B0 and B1. So this is like a general, oh my gosh, the only thing I'm thinking about right now is cake. I don't know why. So this is like a general blank cake, but it's not been filled out with the writing on it to tell like happy birthday to Dr. Florin or something like that. So this is going to be the general standard error of the estimate where we start, and then we're going to add pieces to it. So for instance, when I'm looking at the standard error of B1, I start with the standard error of the estimate, and then I divide by the square root of the sum of x minus x bar squared. So I take this blank starting place, and then I adjust this to be the standard error of B1 specifically, the estimate of B1. So actually, once I add this, remember that our t-tests in general are just the point estimate divided by the standard error. That's all I do. So point estimate over standard error. This is it. Ta-da! And then point estimate over standard error. From here, I'm good to go. So point estimate over standard error, that gives me my t-test. In this case, the point estimate's B1. The standard error is this thing we just looked at. And again, do you need to remember all these details? Well, yeah, you should be able to put this together by hand, but you don't need to like memorize this or anything. Absolutely not. So I want to trace back here. Again, I feel like I may have lost some of you. This is what we need to conduct our test. So this is what I need for my test statistic, and I'm going to compare this to a t-distribution just like we always did. Okay, how do I calculate this? Well, B1, we had a whole slide with the equation for calculating this. S, the standard error of B1, is this s divided by square root of x minus x bar squared. Okay, cool. I can do x minus x bar squared once I have my x values. Where did s come from? S came from the previous slide. It's the square root of the MSE. Where did this MSE come from? Well, the MSE is the sum of squares error over n minus 2. Well, where did the sum of squares error come from? The sum of squares error is y minus the line, so y minus y bar squared. Or if I plug in the equation for the line, which is b0 plus b1x, the minus sign distributes into that, by the way. That's why both of these are minus. You could have minus parentheses, b0 plus b1x, close parentheses, distribute the minus sign in. Anyway, or so if you didn't want to write in the line or didn't want to use the line prediction for every x value, you can just plug in these. So y minus b0 minus b1 times x is where I get the sum of squares error. So I go back a couple of slides to get these with different components being on each slide. But once I go through 2 slides ago and then the last slide, and then I can get to this slide, and then I can calculate this standard error for the slope. Now again, we're going to be doing a two-tailed test, so we compare to the t sub alpha over 2, both on the negative side and the positive side. Remember, it's symmetric, so if I find the value on the positive side, I just give it a negative sign, and it's also the value on the negative side, and I'm looking for the area on the outside of this curve. The p-value I interpret as I always interpret. So my t has a t distribution with n minus 2 degrees of freedom, and again, I'm going to always be comparing these to 0. So again, the process of how I interpret beta 1, the estimate, is I do my significance test, determine if it's different from 0. If it is, then I interpret. So if I have enough information to reject the null, then I can interpret. If I don't, then I don't interpret that particular value for that particular problem and data set. Set my alpha, calculate my test statistic, and then I find my critical value or use my p-value depending on which way is easier. Again, by hand in the notes, I tend to do the critical value. If I have a computer, I use the p-value. So in this particular case, value of the test statistic, 4.63. I don't have a precise p-value, so I'll just compare to the critical value. As this is bigger than the positive critical value, it would have to be bigger than the positive side, smaller than the negative side. This is bigger than the positive critical value. I reject the null hypothesis and take some time to reflect on what that means, to think about, okay, what does that mean to reject the null versus accept the null? So reject the null. The null was that the slope is 0. I have enough information to reject that the slope is 0. What is rejecting that the slope is 0? Well, the alternative is that the slope is not 0. So I have enough evidence to believe that the slope is not 0. And again, this is what's important for interpretation. So if I have a value, let's say beta 1 equals 1,000. Oh my gosh, so big. But the t-test says I don't have enough information to believe that the slope is different from 0. I failed to reject the null hypothesis. I tried to reject that it was 0, but I couldn't. I couldn't reject that it was 0. That is, I couldn't believe it was something else. Well, then I'm not going to interpret a B1 of 1,000 if my hypothesis test tells me that I don't have enough evidence to believe it's different from 0. So all that is saying, if I fail to reject the null, is that 0 could very well be my real slope. I'll say that one more time. If I fail to reject the null, what that tells me is that 0, there is a reasonable chance that 0 could be my slope, or my intercept or whatever. So it doesn't make sense to interpret an intercept or a slope if 0 could be that slope. That is no relationship at all. So I want to make sure that it is statistically significant before I interpret it, because otherwise it doesn't really make any sense to interpret, because it could be 0. It could be no relationship whatsoever, and it would be reasonable to believe that. All right, well, we're getting close. In the next few videos, we're going to go over, in the next video, we're going to go over confidence intervals for the slope, and then we're going to talk about testing the intercept, talk about the overall test, and continue moving on in our discussion of simple linear regression.